Good morning to everyone. Welcome back to another presentation on analogous system, where we have been seeing about the equivalent electrical circuit of for the given mechanical translational systems. Okay, so in today's presentation, we'll see one more example. So directly I will okay, so by the way, this is lecture number 44. We'll see directly one example in this very important example. It is also something like that your mechanical translational system related example, and this is the reference line. This is the reference line. Normally in this particular example you have two blocks actually. This is M1 and one more is also there, one more block. This is M2 mass element, otherwise mass element 1, mass element 2. Here on this force F of t is applied. Okay, so the displacement is x1 here, and here the displacement is x2, because with respect to m1 the displacement is x1, with respect to mass element m2 the displacement is x2, and there is a common spring constant between these two, that is say k1, as well as the frictional coefficient between these two is nothing but it is given as b12. Okay, and here it is given as b1, the frictional coefficient here between this reference and to this, right? So and similarly the other end of this is connected to, this is also reference, and the other end of this m2 is connected with some spring constant k2, and similarly here it is given as the frictional coefficient b2. Clear? So this is the given mechanical translational problem. So carefully see that for this we need to write the force voltage analogy. Force voltage analogy, okay, and force current analogy also. Force current analogy, probably I may cover force voltage analogy in this present video, and then next we will see the force current analogy equivalent of this. Clear? So this is the given mechanical translational block diagram, where you have two mechanical blocks with their mechanical, mass elements as m1, this is m2, and with respect to m1 what are the elements acting on this? So force is applying on this f of t, x1 is displacement, and b1 is there with respect to m1, and k1 is the spring constant between m1 and m2, and b12 is frictional coefficient between these two. Okay, so similarly m2, so these are the different things. With respect to m2, what are the forces acting on this? So the opposing force with respect to m2 will be there, the force due to k2, the force due to b2, the force due to k1, the force due to b2. These are the forces acting. Therefore now we will say that the differential equations. So as I have explained you in the last presentation, so here how many blocks are given? How many blocks are given? So you have two blocks. You have two blocks. So I will write the solution part of it. So solution for this. So as we have two blocks, then definitely you will have two differential equations. Two differential equations. So with respect to M1, you can write the differential equation. The differential equation with respect to displacement x1, or with respect to m1 with respect to mass element, or you can say block 1, yes, you can say with respect to mass element m1, nothing wrong, you can take either block, or otherwise you can take at displacement x1, both are same. So with respect to m1, what are the, how you can write, so you already know how to write, then I can directly give the differential equations. It is m1 into d square x1 by dt square plus, clear. So the force, this is the force opposing by this mass element m1 into d square x by dt square. Then what is there, b1, so it is b1 into dx by dx1 by dt, because for frictional coefficient the first derivative will come. This is also completed. Then k1, what is k1? So k1 is in between, that is common for between those two blocks, that's why. So you can write k1 of into x1 minus x2, as we are considering the block 1, therefore you must write the first displacement, so x1 minus x2, and then b12 plus b12 d by dt of x1 minus x2, x1 minus x2, clear. So m1 we have considered, then this is the b1 we have considered, these two are the common elements, k1 and b1 also we have written, then is equal to your f of t, this is equal to f of t. This is what your f of t, call it as equation number 1. This is the first differential equation, f of t. This is what your f of t. Clear? That is what your f of t. Similarly, with respect to m2, what is the second equation? Similarly, with respect to m2, what you will get? what you will get? So with respect to m2, I will erase this. Erase this, or otherwise, okay, I will write that related expression again here. The differential equation with respect to m2, the differential equation, write that, the differential equation with respect to m2, the differential equation with respect to mass element m2. What is that, tell me? So it is m2 d square x2 now, because we have to consider the displacement x2, dx2 by dt square plus k2 into x2 plus b2 into dx2 by dt plus common elements k1 x2 minus x1 plus b12 d by dt of b12 into d by dt of x2 minus x1 equal to 0, because no force is there upon this. That's why if you consider the first block, all forces, your differential equation, whatever the differential equation comes here, equal to your f of t. F of t is working, or we are applying f of t on this block. Now with respect to m2, there is no force here, that is why equal to 0. You can call it as equation number 2. You can call it as equation number 2, right? So these are the differential equations. Now our aim is to draw the electrical equivalent only, not transfer function. Here our objective is not to find out the transfer function. If the transfer function is given, if it is asked that in the question to find out the transfer function, then you need to apply the Laplace transformation to the both of the equations. For equation number 1 as well as for equation number 2, you need to apply the Laplace transformation, and finally with these two expressions you need to find out the ratio of output by input. Input is your applied force f of t, this is nothing but f of s, whereas the output is x2. You have to consider x2 means the second displacement, that is x2 of s. Therefore for this problem the transfer function is x2 of s by f of s. That you should find out if it is asked to find out the transfer function. But as far as this problem is concerned, here we have to draw the electrical equivalents only in using force voltage analogy, force current voltage, force current analogy. Now for that first of all we need to find out the differential equations like this. Now what we have to do in these expressions, in these two expressions, you need to put the electrical equivalent of mass 2, K2, B2 and like that. So now I can erase this block diagram. Let us see. What is the first expression? What is the first expression we have? The first expression is this one, m1 into d square x1 by dt square plus b1 into d x1 by dt plus, and then k1 into x1 minus x2, I am repeating it, plus b12 into d by dt of, it is x1 minus x2. Clear? That everything is equal to your f of t. This is what your first expression. No? And now you apply for, this is your first expression actually. So just one more time I am writing here for our convenience. Now by using force voltage analogy, what will happen? Your m1 belongs to what? Your m1 belongs to L1. Your okay, directly shall I write? I have remembered that. So your m1 belongs to L1. Similarly b1, it is R1, k1 is equal to 1 by c1. Clear? And x1 is equal to nothing but your x1 is equal to charge q1. Clear? So this is x dot, or otherwise first derivative of it, dx1 by dt, this is equal to further dq1 by dt, further is equal to I. Clear? So as I have explained you in the last presentation, here this is nothing but, as it is a force voltage analogy, you simply remember that V is equal to, as per voltage, we are converting the force to the voltage. Voltage is nothing but V is equal to IR. According to Ohm's law. Therefore, we must write the voltage equivalent of that particular electrical element. That's it. Very simple to understand. We are converting the force, okay, the force or the each mechanical element to the corresponding electrical. In this way, what we are doing is nothing but, for all the electrical element, so you know that M1 is converted as L1, your B1 is converted to R1, K1 is nothing but C1 capacitance, B12 anyhow it is resistance, clear. Therefore, this is nothing but L inductance, this is nothing but your resistance, this is nothing but your capacitance. So then if you consider the inductance, what is the voltage across inductor? That value you must write. Clear? Clear? So this is what actually the meaning of it. Voltage is equal to IR. Voltage, all corresponding, this is inductance basically. It is converted into inductance. This is converted into resistance. B is R, no? It is R. It is L. M is L. Your B is nothing but R. M is nothing but your L. K is equal to capacitance. That's it. That's it. This is capacitance. And finally, B12 is nothing but again resistance, that you can call R12. Like that. Your force becomes voltage, however. Your force becomes voltage, however, because force to voltage. But these are the things actually. Now it is easy basically. If you take L, what is the voltage across L? I will remove this. Okay. I think you got it. This is the simple technique you need to remember. The voltage across each element. Okay. Then say for example, if inductance is there, L, let us say voltage V or V suffix L is the voltage across the inductance. Assume that I is flowing through that. Then what is VL actually? VL, what is the voltage across inductor is equal to L into di by dt. L into. So that is why here L, that is what in general. So where M1 is there, no, your M1 corresponding to L1 actually. If you apply this relation to this particular, this becomes as L1 into X1, nothing but just you write di1 by dt. That's it. This expression becomes your L1 into di1 by dt. Clear? Now tell me, what will be the second? What will be the second? R. B1 is nothing but R1. It is B1, no? Converted into R1. And then tell me, what is the current flowing through that? What is current? So it is resistor. So if you consider resistor R, so voltage across this one is voltage V, and assume that current flowing through this I, according to Ohm's law, V is equal to I into R. Therefore, what is your, actually it is a voltage, therefore I into R. Therefore, obviously, it is nothing but your dx1 by dt is nothing but, what is this? This I only, R1, the R is nothing but your R1. What else is required? I. Therefore, you can write it as I1. So, this dx1 by dt is nothing but I1. Similarly, K1 becomes as 1 by capacitance, 1 by C1. Then tell me, what will happen actually here? What is the current through, okay? What is the current through the capacitor? So, if you see the capacitance, this is capacitance C. Let us see voltage across capacitance V suffix C and assume that current flowing through this I. Then what is VC actually? VC is equal to 1 by C integral of I dt, no? This is what, no? Actually, VC, voltage across. So, 1 by C, nothing but your 1 by C, C1 actually. Then it is nothing but integral of I is nothing but, you have to consider integral as per this. Then it becomes I dt, nothing but I1. The current I is, if you apply this integral to this particular, it becomes I1 minus I2. That's it, into dt. Plus. Then it is R12, again R12, and then what is this actually? I1 minus I2. Clear? And then it is obviously, it is your voltage. It is your voltage. This you can call as some equation number 3. Equation number 3. Clear? Clear? That is what conversion. This is by applying the force voltage analogy, that becomes, this particular becomes like this. And similarly, you apply that force voltage analogy to this expression, the second expression, the expression which we have derived from the second block, that is nothing but this one. If you apply the force voltage analogy for this equation number 2, then that becomes same as this actually. Now M2, what you can write M2? M2 is nothing but your L2, d square x2 by dtt, d square x2 by dt square, nothing but d I2, d I2 of by dt. You can write capital I or small I, nothing wrong in this. It's not this thing. Okay, K2, what is K2? It is 1 by C2. What is X2? X2 is nothing but your integral of I2 into dt plus what is B2? B2 is nothing but R2. What is dx2 by I2? Current. Okay. What is K1? It is 1 by C1 bracket integral of what is x2? I2 minus I1 into dt, clear, plus B12 nothing but your R12, that is I2 minus I1 equal to 0. This you can call it as equation number 4. That's it. Clear? I think you got it. What we are writing here is that we are just writing, this is L2 now. So this is L2 now. This is K2 is capacitance actually. Basically B2 is resistance, R2 we are writing as, K1 are capacitance. Basically this is inductance. Basically remember that this is inductance. This is capacitance. This is the resistance. Again these two are repetition of the same. This is capacitance. This is the resistance however. So this is for inductance. This is nothing but the voltage across inductor. That value come here. This is the voltage across inductor. This is the voltage across capacitor. This is the voltage across resistor. Similarly, like that only. That's it. That's it. That is what the conversion of the mechanical element to the corresponding equivalent electrical element. Clear? Now with the help of these two equations, we draw the electrical equivalent circuit. That's it. If you draw the electrical equivalent by using these two expressions, your problem is over. Now, consider the third equation. Here, normally if you observe, what are the elements you have? R is there, resistance, R, L, okay, here, R is there, L is there, C is there. So, this capacitance, something if you observe that I1 minus I2 means, you can observe that I1, I2 means two currents are there. Similarly, resistance, I1, I2 means that something, these two are the common electrical elements through which I1 and I2 current flowing through that. I1, I2 means if you consider I1 is loop current, first loop current, I1 is the loop current of first loop, whereas I2 definitely it is the loop current flowing through the second loop. So I1, I2 nothing but that is the two currents are flowing through these two elements, nothing but what it's mean. So capacitance C1 and R12 could be the common elements between two loops. So definitely there should be two loops. Electrical circuits, in electrical circuit definitely there should be two loops. In these two loops, these capacitance resistance are the common elements between these two loops. You have to analyze like that. And similarly, if you come to the second equation, L2 is there and it is capacitance is there, R2 is there. It is a simple, only I2 is flowing here. I2, here also I2 is flowing, here also I2 is flowing, means RLC circuit it is, RLC circuit, and again 1 by C1. If you see this 1 by C1, this part and this part, nothing but equivalent to here. These two mean again whatever the common elements is there, no, that common part should come in the both the equations. Okay, so with this, say for example from this third equation, R I1, L I1 means R C, or directly I can write this is a voltage, equal to voltage, means that it is something like this. This is your voltage V of t. This is your voltage V of t. So from this third equation, I can write this. This is R1. This is your R1. This is your L1. And this C1, you can write, this is R is there. You can put R and this is C. This is R12 you can write. This is C1 you can put. First loop is cleared. Now coming to the second loop part, RLC is there. RLC. This is R2. Basically R2 is there. L2. L2 is there. and C2. You can write something like this, no problem. You can. This is your C2. Okay, R, L, C, and 1 by C1, however it came here. R12 is already here, not required to. Now you close this circuit. So assume that this is your I1, this is your I2. You got it? You got it? This is what the electrical equivalent circuit for the given mechanical block actually, mechanical translational system. So this is V of t. If you equate this electrical circuit for compare with this electrical circuit with these two, definitely this is the resultant. So R1, if you, so R1 I1, this is what your R1 I1, L1 into d I1 by dt, nothing but this one, and these two R12 into I1 minus I2, and 1 by C means the voltage across this, definitely this, equal to V of t, your V of t. And coming to this loop, V of t, there is no V of t. So 1, 2, 3, 4, 5 elements will be there. 1, 2, 3, 4, 5. This is whatever equivalent electrical circuit by applying the force voltage analogy for the given translational system. Clear? I think you have enjoyed it definitely, and I think I will finish off this presentation here, and the next part of it, that is force current equivalent force, okay, current equivalent of the given same mechanical translation, we will see in the next subsequent presentation. Okay, thank you one and all, have a nice day.